Shashwat is going to give the talk today morning, the first one. I mean, with a little bit of delay because of, I think, lensing. So he's going to do the single event inference of the environments of binary black hole mergers along with other people. I think there is not much to introduce other than that. Let it start.
First of all, thank you to Chandra and Prayush and the organizers for giving me the opportunity to talk about some of the work that my group does. Now I understand that this is an AI ML workshop. Now in that regard, I just wanted to mention a couple of things. The first is that when initially I was requested to give a talk, I thought that I will just go over all the projects that I have worked on in the past that involve gravitational waves as well as machine learning. So this includes one of the first works that actually showed that you can use machine learning to identify signals from glitches. A work that is currently used by the LVK for rapid communication in low latency of gravitational wave events that could either be EM bright, meaning that they produce electromagnetic counterparts, or EM dark. Another work that is currently used is machine learning. This was led by Shrashti, with her. The idea would be to, given a pair of gravitational wave events, can you tell whether they are they come from the same source and are in fact images of that source or not. A very nice extension of that was presented yesterday by Saurabh. We also looked at, this is work led by Adrit and also Prayush over here, where we looked at whether we can use omega scans to identify circular events versus eccentric events. An extension of that again was presented yesterday. And we can use surrogate modeling to model complicated micro lens systems, and first work in that direction is something that I was also involved in. So these are the works that I have done on machine learning, but what I thought, given that this is also a discussion type workshop, I wanted to speak about one of the thrusts of my group, and in the last two slides I will mention how perhaps machine learning could be introduced, and hopefully this will lead to some discussions later on in the workshop. Now what do I mean exactly by single event inference? We all know that if a gravitational wave event produces an electromagnetic counterpart, you can actually identify where the source came from. You can identify its host galaxy. However, the predominant source that we observe with gravitational waves are binary black hole mergers, and they nominally do not produce electromagnetic counterparts. So the question then becomes, can we actually identify their host environment on a single event basis? And the answer, it turns out, is, at least the current expectation is that you cannot do that. The primary reason is because the localization sky area with gravitational wave detectors is of the order of tens of square degrees at best, and so identifying the exact host galaxy within those tens of square degrees is virtually impossible. Another thing that you could think about is whether there is any signature in the waveform itself, in the shape of the waveform, say in its frequency evolution, that is indicative that it has come from a certain environment or not. And that again, in general, the answer is no. You cannot directly identify what is the host environment, at least today, just by looking at the shape of the waveform. However, I want to now put forward to you two broad methods which in principle could allow you to identify the host environment of a binary black hole merger that does not produce an EM counterpart. And those two methods I have broadly classified as profiling stellar environments and coalescence forensics. Now profiling stellar environments, what I mean by that essentially is that if the motion of the center of mass of the binary black hole, if you have say an acceleration, a line of sight acceleration or a time varying line of sight acceleration, then in principle on a single event basis you can actually reconstruct the gravitational potential within which this center of mass is moving, and that will be the first part of the talk. In the second part of the talk, what I have called coalescence forensics, the idea here is whether through some logical arguments and necessary hypotheses, given that you have a hierarchical merger, whether that automatically gives you some clues about what should be the mass scale of the environment within which the binary black hole merged. Okay. So I will come to the coalescence forensics part in a little bit, but I will start first with profiling stellar environments with gravitational waves. So what is the basic idea here? All right, we all know that if you have a constant velocity motion of the center of mass of a binary, that produces a Doppler shift. Over and above that, you always have the cosmological redshift. However, both of these redshifts are completely degenerate with the source frame mass of the binary black hole. This is the well-known mass redshift degeneracy in gravitational waves. Okay, so that's the first two terms. All right. Now, in principle, you could also have a third source of the redshift, which is the gravitational redshift, and that also is further degenerate with the source frame mass. So what you end up measuring really is just the detector frame mass. What is typically done is to assume that these two are negligible, and then because we measure luminosity distance, we assume a cosmology and we convert the luminosity distance to a cosmological redshift, and that allows us to infer what is the source frame mass. That's the basic idea. Now, I put forward to you one possibility, and that is, what if the Z Doppler were not constant? What if Z Doppler itself was time varying? Say you had an accelerating source. In particular, what if you had a finite component of the acceleration along the line of sight of the observer? In that case, Z Doppler itself would become time varying, and it turns out that because of this time varying Doppler shift, this adds extra modulations on your waveform, and this degeneracy is essentially broken. And you can actually probe the center of mass motion of the binary black hole. All right. So over here, this was actually a GIF, so just imagine these two blue dots over here orbiting a supermassive black hole, and imagine that, say, you are an observer over here. Then you have a projection of the motion along the line of sight, and that becomes time varying as these two blue dots, the binary black hole orbits the larger mass. Okay. Now, is this the only source of line of sight acceleration, say two binary black holes orbiting a central supermassive black hole? The answer is no. There are other sources that could also produce line of sight acceleration. We know, and in fact, we believe that a large fraction of binary black hole mergers should occur in dense stellar environments such as globular clusters or nuclear star clusters, and those dense stellar environments have their own intrinsic potential, which would allow this binary black hole to obtain a finite line of sight acceleration. There could also be what are called hierarchical triples, where you have a compact binary merger, a binary black hole merger, and in the vicinity you have a comparable mass black hole or main sequence star or whatever else that you can think of, and that also could produce a finite line of sight acceleration, and that in principle could be measurable. So those are referred to as in-encounter mergers. So when there is an encounter, so to speak, with a third object, and you have your binary black hole that has merged, then over and above your standard CBC gravitational waveform, you will also have signatures of line of sight acceleration, and in principle higher time derivatives of that line of sight acceleration also. All right, so let us start with the simplest case, which is the case of the binary black hole orbiting a central supermassive black hole in a circular orbit. Then I think using simple Newtonian physics, it is very clear that the magnitude of the acceleration is as given over here, and if you project this acceleration along the line of sight, which is what we have done over here, where angle theta is basically the angle between the line of sight and the acceleration, you project that, multiply it by time. So this is at leading order, there will be higher as well, but at leading order this is what you will get, at cos theta divided by c as your time varying Doppler shift. So moving on, assuming this constant line of sight acceleration, one can actually calculate what will be the corresponding phase difference or phase correction that would be introduced in your post-Newtonian waveform. I really don't need to read out the entire expression, it is very nice and very big and very complicated, but I would like to draw your attention to the leading order over here. So, this gamma that you see is defined as A over C, and notice that it is V raised to minus 13. What this is telling you essentially is that this is a low frequency effect. The lower the frequency, the better your ability to measure this gamma parameter. Okay. So, you would either require your line of sight acceleration to be sufficiently large, in which case you would be able to measure it in today's gravitational wave detectors. Conversely, if you had your line of sight acceleration to be small, you require your detector to be sensitive at low frequencies. Okay, so that's what I am mentioning over here, that you either need a large line of sight acceleration or you need detectors that are sensitive at the low frequency. And in principle, if you could measure this line of sight acceleration, and suppose you assert that the model that I am choosing for my potential is the central Keplerian supermassive black hole, in that case you should be able to put some constraints on the mass of the supermassive black hole as well as the distance between the location of the center of mass and the supermassive black hole. Now, in order to be able to put such constraints, you first need to be able to measure the line of sight acceleration, which shows up as a correction in your post-Newtonian waveform. The standard way to do this, at least today, is to basically sample the gravitational wave parameter estimation likelihood. A number of talks regarding this were presented yesterday, so I don't need to go into details over here, but this is your gravitational wave likelihood. H is your gravitational waveform, S is the detector data, and then you can convert the likelihood to a posterior on the parameters that define the shape of the gravitational waveform, and that you can do using Bayes' theorem. Alright, so what we did for fun over here is we said to ourselves, well, let us see if we can find any signatures of line of sight acceleration in the longest available waveform at the time of publication of this, or at the time of writing of this work, and the longest available waveform in band was essentially GW170817, the binary neutron star merger. So, we decided to look for line of sight acceleration signatures. We did not find any, as you can see that it is completely consistent with 0 A by C. Nevertheless, from the width of this posterior, we were able to put upper limits on the location of the binary neutron star with respect to the center of the galaxy. Now, we know that the binary neutron star merger happened in NGC 4993. We also know the mass of the supermassive black hole in that galaxy, it is 10 to the 8 solar masses, and this allowed us, using this particular equation over here, it allowed us to place a lower limit on the location of the binary with respect to the center of the galaxy, and it was of the order of 10 astronomical units. So, this was the very first gravitational wave based constraint on the location of the binary of on the location of a CBC with respect to the center of a potential. So, while that was very cool, I suppose, the question is how good is this constraint? It turns out that the constraint is fairly modest, which is not surprising given that A by C is a low frequency effect. How modest is it? Well, let us do a comparison. We said that the lower limit on the location should be about 10 astronomical units. Because it was 170817, we actually know the exact location of the binary neutron star with respect to the center of the galaxy is 1.96 kiloparsecs. So, it shows you that this is a relatively weak constraint. However, in the future, what I am going to show you now is that we can do significantly better once we have low frequency gravitational wave detectors, including and especially decihertz, and this will allow us to actually profile stellar environments. So, not just put constraints on the location, but actually reconstruct the gravitational potential. Alright, so first a little bit of Fisher matrix. I think everybody is a GW expert over here, so again I do not need to go into details, but very quickly the Fisher matrix approach is essentially approximating the gravitational wave likelihood as a Gaussian. And then you can identify what are the variances and covariances in your covariance matrix, and from there you can determine what should be the RMS error on the measurement of the line of sight acceleration given a noise power spectral density. So we can noise power spectral densities in this figure. We have A plus PSD, which is the kind of PSD you expect in O5. You have Cosmic Explorer and you have Einstein Telescope. And not surprisingly, as the duration of the signal in band increases, your RMS error on the line of sight acceleration gets better and better. So what you will notice is that at low total masses, you will get much better constraints on A by C. As your mass gets larger, the duration of the signal becomes shorter and your ability to constrain A by C degrades. Nevertheless, with Cosmic Explorer and Einstein Telescope, for binary neutron star like events, you will be able to improve the precision by 3 orders of magnitude relative to what you were able to do with GW17OH17. Moving on, and this is I think one of an excellent science case, I would say, for decihertz, and that is that you will be able to get an RMS error on the line of sight acceleration for binary neutron star like events to be as low as 10 to the minus 16. 10 to the minus 16 per second, so A by C. And even for more massive objects, which you expect to be in dense stellar environments like globular clusters and nuclear star clusters, you can still get excellent RMS errors of the order of 10 to the minus 10 to 10 to the minus 12, as you can see over here. Now, I keep using the word excellent, but what do I exactly mean by excellent? Well, we need to touch base with what you actually expect as line of sight accelerations in, say, dense stellar environments. So what we did in one of our projects is that we looked at the so-called cluster Monte Carlo simulation of globular clusters. We were able to parse that data, and we constructed a distribution of line of sight accelerations from this cluster Monte Carlo simulation. And what you notice is that you can actually detect with decihertz the line of sight accelerations that you would see in globular clusters. So this is very exciting and a very nice science case for decihertz. All right. So this was regarding measuring the line of sight acceleration, but the first part of my talk promised to profile stellar environments. So now I am going to try to convince you that you can indeed profile the stellar environment, whereby profiling I specifically mean reconstruct the potential within which the binary black hole merged. So using this, you can reconstruct the potential of globular clusters, nuclear star clusters, and the Keplerian potential of the supermassive black hole. This came as a very pleasant surprise. And we also later on in hindsight looked at other literature as well, and what is very clear is that if you had a heavy exoplanet that was orbiting one of these binary black holes, then you can also measure the presence of these exoplanets, and that is quite cool because we know that there exist exoplanets in the vicinity of compact binaries. We have seen that within our own galaxy. In fact, the very first exoplanet ever detected was found around a binary pulsar. So we know that these things exist. So if you had heavy exoplanets like Jupiters or super Jupiters, you should be able to know their presence using this method of stellar profiling. And recently we put out a paper where we can reconstruct the gravitational potential of dark matter, provided the binary black hole merged within that dark matter profile. Okay, so there are these questions in the dark matter scenario, whether your dark matter profile is cuspy or spiky, and what implication does that have on the dark matter particle. So in principle, if you did measure or if you did see a binary black hole merger within the dark matter environment, you can reconstruct its potential and you should be able to tell whether it is cuspy or spiky. So what is the key method over here? It's essentially an extension of the line of sight acceleration method, except now in addition to line of sight acceleration, you also have higher time derivatives. You have line of sight jerk, which is the time variation of acceleration. You can have line of sight snap, which is the time variation of jerk, and so on and so forth. So in principle, you can have an entire Taylor expansion like this, and all of this would essentially modulate your waveform through a time varying detector frame mass. And what we basically show is that each of these corrections show up at different post-Newtonian orders. So the line of sight acceleration shows up at a negative 4 pn order, line of sight jerk shows up at a negative 8 pn order, line of sight snap shows up at negative 12, and so on and so forth. So again, you can see as you go to higher time derivatives, you need your detector to be more and more sensitive in the lower frequency domain. And what I will show is that with future detectors, when you become sensitive to that low frequency, because you can measure these higher time derivatives are directly determined from the gravitational potential within which the merger happened, and so you can reconstruct the potential. That's the basic idea. All right, so moving on. So this is what we do. What we do here is, okay, let me go through this carefully. Say you have a binary black hole merger, 30 solar masses occurring at 1 gigaparsec, and let us suppose that this merger happens in a nuclear star cluster. Okay, so then, okay, all right, so let me see if I can, well, I will see how far I can go and then we can decide. So what you can do over here is, by measuring the higher time derivatives of line of sight acceleration, you can reconstruct the free parameters of this gravitational potential. So what are the free parameters here? You have this exponent which you can constrain. You can constrain the mass of the massive black hole at the center of the nuclear star cluster, and you can of course constrain the location of the merger with respect to the center of the potential. So those are the three things that you see over here, and you notice that we can get very good constraints with Decigo. So these are the results for Decigo that we get. Now what I have done over here is I have extended the parameter space. Instead of just looking at a situation where you have one fixed supermassive black hole mass and one fixed location, we vary the location with respect to the center of the potential as well as the mass of the central black hole. And what you notice is that you get RMS errors on the measurements of these parameters, the mass of the black hole as well as r, and as well as the exponent. So here and here and here, so those are your contours. You notice that you get very good RMS errors of the order of 10 to the minus 2, and in principle even 10 to the minus 3 in certain regions of parameter space. All right, so this is regarding the exoplanet claim that I made. So what we do over here is we consider a binary neutron star and a binary black hole. What we then do is we look at the catalog of known exoplanets, and we ask the question, if those exoplanets were orbiting these compact binaries, would they be detectable or not? And how do we decide whether they are detectable? The word detectable or identified here in this work is defined as if we can recover the relative error to within a factor of 2. So that will actually tell you to a good approximation what kind of planet is orbiting the center of mass of these compact objects. And what you notice over here, everything that lies above these lines are effectively identified. And you can notice that a large fraction of these exoplanets, the heavier ones, are being identified using this stellar profiling method. Okay. And finally, this is regarding the dark matter spike and cusp idea, and we wanted to ask if supposing you had a merger within a dark matter spike or cusp, whether we can recover the gravitational potential and its free parameters or not. As you can see, we can actually recover what is the gravitational potential exponent using the stellar profiling method. Okay. Now for certain spikes, this is not very surprising, as the spike index gets larger, your potential gets steeper, and as the steeper the potential, the faster your time variation will be for these different kinematic parameters, and the better you will be able to constrain these spike parameters. So this is not surprising at all. All right. Okay, so I now come to the forensics part. Sanjit, just let me know when I should stop and I will wrap up. Okay?
I think it is okay.
It's okay? All right.
I think the next stop we should start at certainly at 10, what should we say?
No, I think let's stick to the time because
Supposed to start at 10. That is,
that is fine. We can.
I now come to this idea that, okay, I mentioned that we can do very exciting things provided the center of mass of the CBC is moving and provided your gravitational wave detector is sensitive at low frequency, which is not the case today. So is there anything that we can do today that will allow us to measure the mass of the host environment? Can we get any clues about that at all? And what I am going to argue over here is that you can, and this is how you can do it. Okay? There were two events, GW 241011 and GW 241110, that have been argued to be what are called hierarchical mergers. Specifically, they were argued to be what are called 1G plus 2G mergers. So one of the objects is a first generation black hole. So its mass is completely determined by the parent star that collapsed. And the 2G object is a second generation black hole, meaning that in addition to the mass of the stars that produce the black holes, the 2G object over and above involves a former merger, an ancestral merger. Okay? Now it has been argued by the collaboration, and there was a special events collaboration paper that was put out on these two events. Based on circumstantial evidence, it is not a proof, but based on circumstantial evidence, they argued that this is a 1G plus 2G hierarchical merger. So let me start off with this. Let us suppose that this is indeed a 1G plus 2G merger. Then one can actually reconstruct the full story. So what is the story? You have some cluster, say a globular cluster or nuclear star cluster, within which you had the ancestral merger that took place. The merger produced a 2G object which also had a recoil velocity. It then encountered another system, star system, where the 1G object resides. Then there was a swap and the 1G put itself in the place of the star, and then eventually the 1G plus 2G merger occurred. Okay? So this is one possible scenario. Of course, it could be that it need not have been that the companion originally of the 1G object is a star. It could have been something else. It could have been also in a multiple system. It need not have been in a binary. It could have been in a triple system also. The only requirement is that the system that the 2G encounters has to have the 1G object. That's the only requirement. So notice that there are two necessary conditions for which a hierarchical merger of this nature should occur. What are those two conditions? The first condition is that the recoil velocity should be such that it doesn't exceed the escape velocity, meaning that the 2G object should be retained within the cluster. That's condition one. The second condition is that the 2G object had to have encountered another star system, either an isolated 1G object or a 1G object within some star system, a binary, a triple, or whatever, right? So those two are necessary conditions in order for a 1G plus 2G merger to occur. Now what I am going to argue is that because of these two necessary conditions, this automatically gives you a preferred mass scale of the host mass of the globular cluster or nuclear star cluster within which the merger happened. So here's the logical chain of argument. So I start with the Bayesian construction, where I say that I have here my Bayes theorem application. M is the mass of the cluster, H is your hypothesis. So then you need to determine what is the likelihood, which is this term over here. And this likelihood of the hierarchical hypothesis is a combination of two probabilities. You have the retention probability given the mass of the cluster, and then you have the encounter probability given that you have a retention and the mass of the cluster. Now what I have not done over here, and probably for clarity I should have, so I'll just say it, there is also a dependence in the case of retention on the recoil velocity. And this recoil velocity is marginalized with respect to the measured recoil velocity provided by the LVK. Okay? Alright, so once you understand this portion, it is straightforward to see the following. So what we do is we model the cluster as a Plummer sphere. which is a nice analytical baseline model. And it is applicable to non-cuspy nuclear star clusters as well as globular clusters. And it is known from observation that the scale radius of the Plummer sphere for globular clusters and nuclear star clusters have a scaling with mass, which is very well modeled as this particular scaling. And this beta parameter has been provided by observation. Okay? So these are a set of assumptions. Now there are additional assumptions on the encounter. What we assume is what are called strong encounters. So essentially we assume that the relative velocity between the center of mass of the star system and the center of mass of the 2G object, that relative velocity is much smaller than the orbital velocity of the star system, the typical orbital velocity. And we also assume that the 2G remnant, after it has acquired its recoil and before it has encountered, over a period of time it has effectively thermalized, meaning that it has no memory of the recoil velocity. So assuming these two things, one can actually construct the two probabilities, recoil velocity hypothesis probability as well as encounter probability. Okay? Alright, so this is essentially how you would construct the probability that there was a retention. The integral that's doing the heavy work over here is the last one, which involves the theta function. In words, in human language, this is essentially counting the fraction of events where the total velocity, which is the sum of the thermal velocity of the center of mass as well as the recoil velocity, their sum, the magnitude, has to be less than the escape velocity. So, and then you marginalize out with respect to the thermal distribution of velocities in a Plummer sphere as well as the radial distribution of objects in a Plummer sphere. Now, the retention probability. You can similarly do something with the encounter probability. So, over here I have the encounter rate, which is a combination of three factors. You have the number density of objects, you have the cross section, and then you have the relative velocity between the center of mass of the star system and the 2G object. 2 minutes? Okay. Now, what you notice over here is that this term, the encounter rate, by itself doesn't give you a probability. You need to first multiply it by time and then assume that these things happen as a Poisson process, and then the probability of having at least one encounter would be 1 minus gamma into t put in the exponential. So, 1 minus exponential minus gamma into t. That is formally the probability of encounter. However, what has been shown, and this is something that you can check for yourselves, is that per cluster, gamma into t, when t can be as large as 1 giga-year as well, the per cluster encounter rate is actually very tiny. And therefore, to a very good approximation, you can take this approximation, encounter rate into time much less than 1. So, effectively your encounter probability is just gamma into t. Now, once you have this nice approximation, what you notice is that a number of the nuisance parameters that go into evaluating these, they essentially scale out as a constant factor. And then when you marginalize out with respect to the Plummer radial distribution as well as the Plummer velocity distribution, you get this very nice scaling of the encounter probability as a function of mass of the cluster. So now what you can do is you can combine the two and you can determine what is the likelihood of a hierarchical merger, and then you can marginalize out with respect to the recoil velocity provided by the LVK, and then you can essentially get what is the posterior on the mass of the cluster. So this slide I will just skip. This is just telling you what are the typical sensitivities to the inputs. So the sensitivity of the posterior to the inputs of that come from the outside. So for example, how sensitive is the peak of the posterior to the recoil velocity, how sensitive is the peak to the scale radius under different assumptions of the beta parameter. So I won't go into all the details here. I'll just quickly come to the main result, and the main result over here is as follows. There were two sets of recoil velocity posteriors that were made available, the so-called forwards method which is essentially a set of priors that were assumed for the construction of the recoil velocity and provided by the LVK. And there was another set of posteriors that were provided using the so-called backwards method. They just differ from each other on the choice of priors. And based on these priors, we were able to get what is the preferred mass scale. So what is the posterior on the mass of the cluster, I will not read out these numbers, but basically the qualitative summary is that the recovered mass of the environment of the globular cluster is consistent with either a heavy globular cluster or a nuclear star cluster. Okay. Alright, so these are the visual representations of the posteriors on the mass of the cluster. This is for GW 241011, this is for GW 241110. At order of magnitude they are very similar, which is not surprising given that the recoil velocity posteriors were also very similar they were very similar to each other between the two events 241110 and GW 241011. Alright, so I come to my summary. So essentially we have two methods. One is a profiling method and one we have this coalescence forensics method that allow you to determine what is the environment within which the binary black hole merged. The profiling method is much more powerful in the sense that you can reconstruct the potential, but even using forensics and using current data, in principle you can get a preferred mass scale of the environment within the environment within which the object merged. So what I want to do over here is just list a set of points involving machine learning where this could improve. Now the clever audience I'm sure would have noticed that a lot of, so for the first part of the talk the entire analysis was done using Fisher matrix. What you require eventually, if you did see line of sight acceleration and jerk and snap, you would require large scale parameter estimation exercises that will require rapid parameter estimation as well as precise parameter estimation. So I think that is crucial in order for the profiling method to work. What I believe would be extremely useful for the forensics method is to also incorporate other features that affect the structure of your environment, such as metallicity, mass segregation, equipartition of energy. So all of these things have to be self-consistently simulated and then input into your Bayesian framework. So if there were a machine learning way to actually do this, where one can rapidly simulate these cluster Monte Carlo like simulations, or conversely using the outputs of cluster Monte Carlo simulation, whether one can come up with good mappings between these parameters that define the structure and the posterior, I think that would be very useful. So okay, thanks a lot and thank you for entertaining my overshooting.